Hey dear class, in this video we're going to talk about polar coordinates. So a polar coordinate is another way to describe a point different from a rectangular coordinate. So in rectangular coordinates we have a point in space and we describe that point with an xy pair, and this is how the x is how far I have to go over to the right, and then the y coordinate is how far I have to go up to get to that point. And that's why they're, most of the time they're called rectangular coordinates, because I have these two different paths to get to that point, and the two paths create a rectangle. But with polar coordinates, what I would do instead is I would extend out how far I want to go. Like if I want to go to like this point, for instance, I would go that same distance, like from the origin to that point, whatever that distance is, I would go that far on the x-axis, or what we call the polar axis, and then I would rotate at the pole, which is the origin typically, until I got to that point. I would rotate by some angle theta, and with this r, the radius of the circle I'm on, went out this far and I'm rotating, I'm still that same distance. So basically it's like the radius of a circle. We would label this point now r theta, r being how far out along the x-axis I have to go out to get to the point I want to get to, and then theta, the angle of rotation I have to rotate to get there. So it's basically another way to describe points in the plane that doesn't use rectangles. It uses circles to get there. So when you are in, this is in Desmos. Desmos has over here with the the wrench tool, it has a way to change your grid from rectangular coordinates, Cartesian coordinates, to polar coordinates, which is that little one that's right beside the rectangular grid. That's the polar grid. And we can see angle measures on there. There's pi over 6, pi over 3, there's pi over 4 right in the middle. And then these are r's, these are distances. And you can see if we go all the way around, it makes these circles. So that's what a polar grid looks like. So the first objective is just going to be plotting points, just getting used to that procedure to plot a point. So we start off with if we start off with a positive r, we're going to extend into the positive x direction and then rotate by whatever the angle is. That's the procedure for a polar coordinate. All right, here is 2 and 4 pi over 3. So we go out 2 units, then rotate 4 pi over 3 units. So again, there's my 2 circle in Desmos. I'm going to kind of zoom in to make that circle more prominent. So there I'm on the 2 circle, so I kind of start there, and then I'd rotate all the way around. There's 4 pi over 3. It comes to that point right there. So that point literally is me starting from there and rotating all the way around to that point. And that point is 4 pi over 3. All right, 2 negative pi over 3. Again, there's the 2 mark on the tick mark. Pi over 3, notice that's 1, 2, 3, 4 tick marks up this way. So if I went 4 in the other way, 1, 2, 3, 4, that's 5 pi over 3. That's the same as negative pi over 3. So I'd end up right there, and that would be the point 2 negative pi over 3. Notice it's the same thing as if it were 2 positive 5 pi over 3. That would be me rotating all the way around 2 pi. Well, I can do that again, and have 11 pi over 3. I can do it again and have 17 pi over 3. There's not one way to get a polar coordinate because of that, because I could keep rotating around over and over and over again in the positive or negative direction. All right, there's one way, if I want the point 1, 1, there it is. There's just one way to get the point 1, 1. But in a polar form, there's infinitely many ways to describe that point with a pair, a radius, and an angle. And it's because of that infinitely many angles that we can get there. All right, there's actually multiple representations with the radius, but we'll talk about that in just a little bit. All right, notice 2, 0, the polar point is the same as 2, 0 with the rectangular coordinate. It's 2 units to the right and 0 units up with rectangular coordinates. Well, it's a radius of 2, a distance of 2 from the origin without rotating. And because we start on the positive x-axis, they actually look the same. All right, here's the big one. When we have a negative r, we rotate by what positive r would be. So negative pi over 3, we've already seen that one. That would be rotating down here. But instead of going in the forward direction, we go in the backward, opposite direction, 3 units. All right, so let me get my 3 circle in the picture. There's my 3 circle. So we've already seen that negative pi over 3 is the same thing as positive 5 pi over 3. I would be here. If it were a positive r, I'd be at the pole and I would point out in that direction. I'd move forward r units. But because it's a negative r, it's like we're facing in that direction. But then we walk backwards along that same line. I'm going to dash it. But we go through that same line through the origin out until we hit this same radius on the other side. And that is negative 3 negative pi over 3. So that is a negative angle because we went this way pi over 3 units. And then once I've rotated and pointed in the correct direction, instead of moving forward, I move backwards from the direction that I'm facing, and I walk backwards 3 units. So that's what you got to get used to when you are dealing with a r value that's negative. All right, this slide is just talking about how there's more than one representation of a polar coordinate. So 3 positive pi over 6. So there, I'm on the 3 circle. There's pi over 6. But if I went all the way around an additional 2 pi, now instead of pi over 6, that's pi over 6 plus 2 pi, which is the same as 12 pi over 6. That would be 13 pi over 6 if I went all the way around. But it would also be, if I went back the other way, 2 pi radians, that would be pi over 6 minus 12 pi, which would be negative 11 pi over 6. And so any of those angles paired with the number 3 would give me a representation of that point. All right, and then again, I could just keep going around 2 pi in either direction. All right, but it also mentions, in addition to that, there's pi over 6. If I follow that line and come out the other side, I'd come out here at 7 pi over 6. So if I rotated to 7 pi over 6, but then used a negative 3, I would also end up at that point. So I could use a negative number for the r and add pi radians to where I currently am. So I'm adding pi radians and then negating it, and I would also end up at that point. All right, and then from negative 3, 7 pi over 6, I could add 2 pi to 7 pi over 6, subtract 2 pi from 7 pi over 6, and I would have infinitely many versions of that procedure with a negative number there. So it's just not unique. A polar coordinate is not a unique value. All right, so they're going to have you do with specific values, specific numbers. So 2 and pi over 3 is our polar coordinate. So there's 2, there's pi over 3, so there is a point that we're starting with. And then it says, find one where r is positive and we're between 2 pi and 4 pi. So remember, 0 to 2 pi is the first revolution. So this is adding another 2 pi to get the second revolution. So if I add 2 pi to this, I would go from here all the way around back to where I am. So pi over 3 plus 2 pi again. Pi over 3, 2 pi would be 6 pi over 3 with 3 as a common denominator. So pi over 3 plus 6 pi over 3 would be 7 pi over 3. And so 2 comma 7 pi over 3 fits the criteria here. All right, for the second one, r is negative, and we're within the first revolution on the unit circle. All right, for r to be negative, again, you're going to need to go through the origin. So follow that line. You'll end up at 4 pi over 3. Again, you're just adding pi over 3 to that. So 4 pi over 3 with 2 would give me here. If I negate it, I would be right back to there where I was. So that's going to be a negative 2 and 4 pi over 3. All right, now we're back to r being positive, but we have a negative angle. So we can start with our original 2 pi over 3 and just subtract 2 pi instead of adding 2 pi like we did here. So 6 pi over 3 subtracted from pi over 3 would be a negative 5 pi over 3. So let's just kind of recap. What did we do? We added 2 pi to this, we got that one. We subtracted 2 pi from this, and we got this one. If we added just pi to this, then we got 4 pi over 3, which made us need to negate the value for r. All right, if we want to convert from polar to rectangular, we take our angle that's given to us, we take our r, and we plug into these formulas. X equals r cosine theta, x equals r sine theta, or sorry, y equals r sine theta. That'll give us the x and y coordinates of a point if we were given r and theta versions of those point coordinates. All right, 2 pi over 4, that's my r, that's my theta. So I'm going to replace in both of these formulas r with 2, theta with pi over 4. All right, so r is 2. 2 times the cosine of pi over 4 is 2 times the square root of 2. The 2's cancel, we're left with the square root of 2. And the same thing's going to happen with the y coordinate because pi over 4 is 45 degrees, x equals y there in quadrant 1. So there's where we end up. Now, when we have this negative out here, we don't have to do anything special. The multiplication and stuff will take care of the signs in the conversion. So you just grab the -2, put it in there where the r is, grab the -π/6, put it in there where the sine and cosine are. Alright, the cosine of -π/6 is the positive square root of 3/2. Alright, if you don't know that, again, that's where your unit circle can come in. There's π/6, -π/6 would be in the other direction. Cosine's the x-coordinate, so there's the square root of 3/2. Alright, for y, the sine of -π/6, there's π/6, -π/6 would be here. The sine is -1/2. So that's where these two numbers are coming from. And then when we simplify, we get that. So just make sure that you have these two down pat. Okay, it's just coming, again, this is all just coming from circles. If I draw a circle centered at the origin, right, and that circle has a radius of r, sorry for this chicken scratch, right, that's the x-coordinate, the y-coordinate, right? Well, if I drop a perpendicular, and there's my angle that I rotated, that creates a right triangle. And that right triangle has an hypotenuse r. The opposite side is y. And the adjacent side is x. And so remember, cosine is x over r, adjacent over hypotenuse. So if cosine is x over r, multiply that by r, and you get x equals r cosine theta. Same with y. Opposite over hypotenuse, multiply by r, you get y equals r sine theta. It's just straight up coming from a circle radius r and right triangle trig. All right, what if I am converting between rectangular, starting with a rectangular and converting to polar? Well, you just have to remember what we're doing. We're finding the distance that point is from the origin. So if I'm on the y-axis, it's 2 units away. And then I'm asking how much did I rotate from the x-axis to get to the y-axis. So I rotated 90 degrees, or pi/2 radians. So that makes this point in polar coordinates 2, pi/2. Right? But again, there's not a single representation. We could have had multiple different values and still end up at that same point. So the conversion between polar to rectangular is there's just one way. There's just one rectangular coordinate we'll get. But when we start with rectangular and go to polar, we have infinitely many possibilities. Typically, you want one with the smallest positive angle and a positive value for r. And when that's the case, in this case, it would have been the 2 pi/2. All right, what if my point is 3, -3? So I'm in quadrant 4. The first thing I want to do is calculate r, because remember, we need r and theta. So r can be found with the Pythagorean theorem, 3 and 3 as the legs of this triangle. So by the Pythagorean theorem, this would be 3 times the square root of 2. And then to get theta, well, the x-coordinate is 3, the y-coordinate is -3. Y divided by x, the slope of this little line segment, is -3 divided by 3, -1. And so the inverse tangent of -1 would be -45 degrees, or -pi/4. But if I want it to be between 0 and 2 pi, for instance, I would need to add 2 pi to this. I'm sorry, I would need to add, yes, 2 pi to this, which would give me 7 pi/4. So I could do that one. If I added just pi to this, and I got 3 pi/4, remember, I would need to negate that. So either one of those is fine if we want a positive angle, but this would be the one that the unit, like it would show up on the unit circle. The 7 pi/4 would, and be at the same location as this point. All right, so there is what we end up using. Our textbook says when we have, when we don't know the angle, we always use the inverse tangent. I actually use my unit circle. And what I mean by that is, like in this procedure where it's asking if I have the point -2, -2. Well, -2, -2, that's going to be in quadrant 3. And the x and y coordinates are the same. So in quadrant 3, where the x and y coordinates are the same, that's 5 pi/4. So I'm not using inverse tangent to do that. I'm just looking on the unit circle where those things that I need to have happen are happening. So you can use the inverse tangent and add the pi and make adjustments based on which quadrant you're in, which is what this is showing us. But you can also just use the unit circle and find the angles in those quadrants. All right, let me show you where this formula is coming from that's being used in this problem. So again, if I have a circle of radius r, pretend that's a circle. There's r. If I drop that perpendicular, that's the point xy that's on that circle of radius r. If I drop that perpendicular, again, I get a right triangle, and we end up with the Pythagorean theorem applying to x, y, and r. And it's x squared plus y squared equals r squared. And so right here in the work where r squared is, and then the next line is x squared plus y squared, it's literally this. It's just the Pythagorean theorem applied to x, y, and r. So when you see a situation like this, r equals something times cosine, we want to use these for the x equals r cosine theta, x equals r sine theta to get back to x and y. So when I see 4 cosine theta, I almost see r cosine theta. So that's why we're multiplying both sides of this equation by r. So we're multiplying there, getting r squared. There's no r here. Now we do have one. We multiplied the left and right by r to create 4 cosine theta. And now that we have it, r cosine theta is just x. All right, so now we can see that once we've done all that, this is going to end up being a circle. Okay, so we're going to keep going with it to make sure that we can center the circle. 1x squared, 1y squared, that's going to be a circle. All right, but we move the 4x over to join the x squared, and this is called completing the square. If that procedure right here doesn't make sense to you, you need to search completing the square and watch some videos on that to where you can get good at that, because we're going to need that in this transformation from polar to rectangular. So this is a circle. The center is what makes this equal to 0, 2 does, and then this is just y, so 0 makes y 0. So 2 makes x 0, 0 makes y 0. That's the center of our circle. And then this radius is 2 because the square root of 4 is 2. Right, this is x squared plus y squared equals r squared. Right, so the radius squared is 4, so the radius was 2. All right, and then if I want to go from rectangular to polar, x's and y's are replaced with r cosine theta and y r sine theta respectively. So this x becomes r cosine theta, this y becomes r sine theta. Multiplying them together, I have an r squared cosine theta sine theta. All right, and then just notice I can switch, I can break this 4 up into 2 times 2, give 2 to cosine theta sine theta, and that's a double angle identity. That is the sine of 2 theta. And now we have something written in polar form. And all we're doing, again, the original equation had x's and y's together in an equation, and we're coming up with an equivalent form that has r's and thetas in the equation. They're both the same collection of points. It's just this one's defined in a polar form, whereas the original was defined with rectangular.